Hey everyone, and welcome to this explainer. I'm really thrilled you're joining me today. If you're the kind of focused learner who absolutely loves breaking down massive, complex engineering marvels into clear, understandable pieces, well, you are in exactly the right place. Today, we're going to be zooming out and then zooming way, way in on a technology that has literally redefined how we move across continents. We are talking, of course, about the incredible world of high-speed rail. But, before we get into the actual nuts and bolts of how these things work, I want to pose a slightly counterintuitive math puzzle to you, straight from our source material. Why in the world would a traveler, or a whole society really, choose to build and ride a train that maxes out at, say, 360 kilometers per hour, over a commercial jet that effortlessly cruises at 900 kilometers per hour? I mean, on paper, the airplane is nearly 3 times faster, right? And yet, in many parts of the world, high-speed rail is absolutely dominating airlines on key routes. How does that math actually work? Keep that paradox in your mind, because solving it really unlocks the entire logic of this industry.
So, here's our roadmap for this explainer today. First, we'll look at the historical quest for speed. Second, we'll dissect the actual anatomy of high-speed rail. Third, we'll check out the global pioneers who built all this. And finally, we'll answer that opening riddle by pitting rail directly against commercial flight. All right, let's jump right into Module 1, the quest for speed. We're mapping historical travel velocity here because, let's face it, wanting to get somewhere faster is pretty much baked into human nature.
And looking at the history of travel, you can clearly see that desire to constantly push the limits across different modes of transit. Aviation obviously made a massive, sudden leap and then basically leveled off at those high cruising speeds. But take a look at the trajectory for trains. That line has been climbing steadily upwards for decades. Engineers just keep finding new breakthroughs to push the absolute physical limits of what we can do on the ground. Yeah, the contrast between road and rail is super fascinating. Have you ever noticed that cars haven't actually gotten legally faster in decades? Basically, road speeds have stabilized globally between 90 to 130 kilometers per hour. We've kind of hit a human and safety ceiling on highways. But rail speed records? Totally different story. They just keep aggressively evolving. Modern commercial high-speed rail routinely hits up to 360 kilometers per hour. To go that fast safely, we literally had to take the steering wheel out of human hands and put it on a dedicated track.
Which brings us perfectly into Module 2, the anatomy of high-speed rail. Because the main takeaway here is that high-speed rail is so much more than just a regular train strapped to a bigger engine.
It's actually an incredibly complex, fully integrated ecosystem. A high-speed railway demands state-of-the-art synergy across a bunch of moving parts. Yes, you need specialized infrastructure, like ultra-flat, straight tracks, and you need advanced rolling stock, which are the trains themselves. But you also need completely specialized operation rules and high-tech signaling systems, because human eyes literally cannot process track signals at 300 kilometers an hour. Plus, you've got rigorous maintenance, complex financing, and intense legal frameworks to manage. If even one of these pieces fails, the whole network grinds to a halt. It's a total marvel of systemic engineering.
And all of that mind-boggling engineering is really aimed at optimizing one specific thing. And spoiler alert, it is not just top speed. Our source points out a crucial distinction here. You have commercial speed, which is just traveling at a high rate of velocity, but then you have total time of travel, which is your overall journey time from your front door to your final destination door. As a passenger, you only really care about that second one, right? I mean, it doesn't matter if you moved at Mach 1 for 10 minutes if it took you 3 tedious hours just to get onto the vehicle. So high-speed rail specifically attacks that total time of travel by mastering a few key performance factors. Think about these massive customer benefits. You have high frequency, meaning you aren't planning your whole day around one single departure. You've got extreme reliability, that's totally independent of weather. A rainstorm or heavy fog isn't going to ground a train the way it grounds a plane. They're incredibly easy to access, and the absolute best part? No long, soul-crushing check-in processes. You literally just walk onto the platform, find your seat, and you're off. Okay, let's move into Section 3 and see how this all plays out in the real world. We're looking at the global high-speed pioneers, the nations that actually built the future. Historically speaking, Japan was the absolute trailblazer here. They launched the legendary Shinkansen, or bullet train, way back in 1964. And honestly, that achievement sent absolute shockwaves through the engineering world. It kicked off a massive European race. France is quick to follow, running TGV trials at a blistering 318 kilometers per hour by 1967. Then Germany jumped into the high-speed commercial era in 1991 with their IC lines. And Italy started taking on some massive engineering feats to build out their network in 1996.
But I really want to pause on Japan for a second because this statistic from the text is just wild. 50. Back in 2014, Japan celebrated 50 years of Shinkansen service. Over those 5 decades, carrying billions, yes, billions of passengers at those crazy speeds, they had exactly 0 fatalities. 0. And their average delay per train was less than 1 minute. That right there is the ultimate proof of that perfectly integrated ecosystem we talked about earlier working in total harmony. And visually, the evolution of these trains is pretty striking. On one hand, you've got the super distinct, highly aerodynamic profile of the Japanese Shinkansen, and on the other, the iconic French TGV. And the TGV was a massive, massive success. The launch of lines like the Atlantic TGV practically opened up the entire western half of France, quickly hitting 20 million riders a year. Both of these nations basically proved that high-speed rail wasn't some flashy novelty. It was a fundamental, game-changing upgrade to national infrastructure. Meanwhile, Germany was busy developing their own ICE program. When they launched the ICE-1 trains in 1991 on routes between Hanover and Würzburg, it instantly shaved a full 2 hours off the journey times. Just imagine getting 2 hours of your life back every single time you travel across the country. That's the real transformative power of this tech. But we have to acknowledge that building this stuff is not easy, and it is definitely not cheap. For example, to build a 79-kilometer line between Bologna and Florence, Italy, had to dig 72 kilometers of tunnels straight through the Apennine Mountains. That means 90% of the entire route is underground. It perfectly illustrates the immense geographical hurdles and the astronomical financial costs of creating those perfectly flat, straight tracks that high-speed trains demand. Which brings us to our 4th and final module, rail versus commercial flight. It's time to finally solve that opening riddle. The answer to why a slower train beats a faster plane actually comes down to urban geography. Think about it. Airports are huge, often covering several square kilometers, so they have to be built way out in the suburbs or even further. Getting there usually means a 60-minute commute before you even look at an airplane. But train stations? For historical reasons, they're super compact and located right smack in the middle of city centers. Even in dense urban grids, we can just build them underground. You don't have to commute out of the city just to start your trip. Let's look at the hard data for the famous London to Paris route. The Eurostar train tops out at about 300 kilometers per hour, while a commercial flight is cruising at roughly 900 kilometers per hour. Now, the stated flight time is an incredibly quick 45 minutes compared to the train's 2 hours and 30 minutes. But, and this is the absolute kicker, look at that final column. When you calculate the total point-to-point time, that means city center to city center, factoring in the commute to the airport, security, and boarding, the airline journey actually takes 3 hours. The highly engineered train steals the market simply because it gives you 30 minutes of your life back. And beyond just saving time, there is a staggering difference in energy efficiency. If a journey by train uses 1 unit of energy, that exact same journey by car consumes 4 times as much. And by plane, a plane consumes 9 times the energy. The amount of raw power required just to fight gravity and keep a heavy metal tube up in the sky is absolutely immense. The secret behind this incredible efficiency is pure physics. Our source notes that once a train is moving, even if the engines are switched off, the train does not even decelerate noticeably, even at very high speeds. That is the magic of steel wheels rolling on steel tracks. The friction is just so incredibly low that the train uses its own massive momentum to basically coast at breakneck speeds. It requires very little continuous energy to keep that velocity going. So that leaves us with a pretty provocative thought to wrap things up. As these high-speed rail networks keep expanding and connecting across continents, delivering you door-to-door faster, safer, and using 9 times less energy, well, will short-haul flying simply become a thing of the past? Based on everything we've unpacked today, I'd say it's a question the aviation industry needs to be taking very, very seriously. Thanks so much for joining me for this explainer. Keep learning, stay curious, and I'll catch you next.